We've learned that if we take two positive charges, they will repel each other. This force is called the Coulomb force, but it also has other names. We sometimes call it the electrostatic force, or we might also call it just the electric force. We know that the electric force is calculated using this equation, which is called Coulomb's law. But where does the force actually come from? How is this charge getting pushed when it's not touching anything? We say that the charge is being pushed by an electric field. The electric field permeates all of space, and the field is what does the pushing. This charge is also in the electric field, so why does it get pushed? Because the field is what pushes it. Now there's a couple questions we're going to want to ask. The first is, what does this field do? What's the impact of the field? And we already kind of know the answer. The second question is, where does this field come from? One way to answer this is, it's a property of space. But we're going to take a look at that after this video at a different time. We can't answer this question just yet. First, we have other things to learn. But the first question we do know the answer to. What does the field do? It pushes on charges. Let's explore this idea of an electric field a little bit more. Let's say you take a charge and you put it at this point in space. This charge maybe feels a force that looks like this. But then, if you take the same charge and you put it over here, it feels a force like that. So we see that the electric field is not always the same at every point. There are some places where it's strong, some places where it's weak. What is this little positive charge? This is just a small positive test charge, which I'm using to test out the field at different locations. Now, the small positive test charge is so small that the charge is not impacting the field anywhere. What we've seen is that this electric field has varying strength. Some places it's strong, in other locations it's weak. So we use this quantity, electric field strength, to distinguish the strength of the field at different locations. Where the field is stronger, it pushes harder. That's our rule. So take your small positive test charge, and let's say you put it right here. And at this location, the force it feels is this. We define the electric field strength. We define E, the electric field strength, as the force on our small positive test charge divided by the amount of coulombs in the test charge. Let's take a closer look at what this electric field strength means. When we put our charge at a location, it doesn't have to have a force that's horizontal. The force could be at an angle. Now let's say that at this location the field strength is 2 newtons per coulomb. What does that mean? Well, if the charge has 12 coulombs, we can zoom in and understand this a little better. So I've zoomed in. This one charge has 12 coulombs, so we could break it into chunks. Every 1 coulomb per coulomb, there is a 2 Newton force. So this 1 coulomb feels a 2 Newton force, and so does this one and that one. Every 1 coulomb in this test charge feels 2 newtons of force. So what's the total force going to be? Well, you've got 12 coulombs, every one feels 2 newtons, so the total is 24 newtons. But we could use the equation to calculate this too. The electric field strength is the force on a test charge divided by how many coulombs in the test charge. So we plug in 2 newtons per coulomb as the field strength. We plug in 12 coulombs for the charge, and you calculate F to be 24. Let's recap what we know so far. We use electric field strength to talk about the field. It helps us distinguish weak points from strong points. When we measure electric field strength, we use a small positive test charge. We define it as the force on the test charge divided by how many coulombs in the charge. So we know it has a magnitude equal to this amount, and it also has a direction. Electric field strength is a vector. Here's how you find the direction. The rule is that the field points parallel to the force on our positive test charge. So let's say we put our positive test charge right here, and we feel a force pointing to the left. If the force points to the left, then so does the electric field strength. Now, why did my field strength arrow get smaller? Because I divided by some charge to get this value. So this equation tells us how to find the magnitude of the field strength, and this rule tells us how to find the direction.